This problem illustrates the principle of the conservation of energy. In this problem, we're going to have a ball, let it roll down a track, and the question is, can it make it around the loop? We'll assume that there's no friction, which is an important assumption here because we can't use the conservation of energy if we have any non-conservative forces such as friction. Also, if there is no friction, then we don't need to know what the angle of the ramp is or what the geometry of the curve at the bottom is. The only thing that's going to be important is how high do we drop it from. Now let's go ahead and look at simulation of this in SolidWorks Motion. And so I've picked an arbitrary height of 50 feet here, and you can see the ball rolls around with no problem. I made the track transparent so you can see it a little better. And again, arbitrarily went down to a much lower height of 30 feet, and you can see there's not enough speed to get around the loop. So let's see if we can figure out exactly what speed that we do need. Well, we need to know something about the geometry of the loop. You can see that the radius of curvature here of the path that the ball is going to take is 14.25 feet, so the overall height of the loop is 28 feet. So when we dropped it from a little bit higher than that, 30 feet, that didn't make it. So we're going to need some velocity at the top of the loop to be able to make it around, and we'll calculate that in just a moment. Just point out here, this is not really a planar path that it's traveling around, because it is moving in the third dimension, the one perpendicular to the screen here. But that dimension is small compared to the radius, and so idealizing the plane as the path as planar is a good assumption here. Now, what speed are we going to need at the top of the loop to be able to make that circular path and to make sure we don't separate from the path itself or from the track? Well, if we draw a free body diagram of the ball at the top of the loop, certainly we have the weight acting downward, and as long as we're in contact with the track, there will be a normal force between the ball and the track. And both of those will be in the direction of the center of curvature, or toward the center of curvature, so in other words, in the normal direction. And so when we take the sum of the forces in that direction, we have the normal force and the weight both acting toward the center of curvature equals to the mass times the normal acceleration. And so we can write that as an expression for the normal force, and now substitute in for the normal acceleration. We know for a curved path that the normal acceleration is v squared over rho, the radius of curvature, and we write the weight as mg. Now, the normal force is going to be positive as long as there's contact, and if it goes to zero, of course it can't really go negative because there's no way to create a tensile force between there. But if it's exactly zero, then we're just almost separating at that point. So to find the minimum speed that's required to get around the loop, we want to set n equal to 0 and find the velocity corresponding to that. And of course the mass will cancel out, so it doesn't matter how heavy the ball is for this problem. And then the speed comes out to 21.4 feet per second. So going back and look at the equation for n, you can see if the speed is greater than that, then we're going to have a positive n, which means that there's always going to be a normal force. There's always going to be contact between the ball and the track. If we let it go less than that, then we won't be able to maintain the acceleration that's required for it to maintain a circular path. So height 1 is what we're trying to find. That's where we need to drop it from. Height 2 is when we're at the top of the loop. And so now we can apply conservation of energy. At position 1, at the start, we're dropping it from rest, so the kinetic energy is equal to 0, and the potential energy is the weight times the height, or mgh1. At the top of the loop, we have a kinetic energy 1/2 mv2 squared, and v2 would be the velocity we just found, the minimum velocity required to make it around the loop. and the potential energy will be the weight times h2, and h2 is just 28.5 feet we just talked about. So we know the conditions at the top of the loop, we know everything except for h1, and so now we apply the equations that the initial kinetic energy plus potential energy is equal to the potential energy and kinetic energy at the top of the loop. And once again we see that m is going to cancel out from all the terms, so the mass isn't important. And so we go through the calculations and we find that h1 is 35.6 feet. Okay. So we'll go back to our SolidWorks simulation and we'll run it for 35.6 feet. And you can see we do navigate the loop okay. And if we take a look at the velocity profile here, we can see that the velocity does drop down to 21 to 22 feet per second when we're at the top of the loop, which is the calculated value we have of the minimum speed for which there would be no separation. Now if we go a little bit less than that, so dropping it down to 34 feet, again just a little below our calculated value, then our prediction is we shouldn't be able to make it around the loop. And you can see that we actually do, but you probably saw what happened there as well. And if we look at it in slow motion and change the view a little bit, you can see it better. What will happen here is that there is not enough speed at the top of the loop to maintain contact, to maintain a positive normal force. And so what will happen is that the ball will actually become a projectile from right about here and then land again on the track and be able to make it all the way around. If we look at the velocity profile here, you can see that our velocity actually, as we said, went down below 20 feet per second, so below the minimum value required to maintain a normal force with the track. And you also see everything smooth except for this point right here, and if we look at what happens there, that's actually you can see the ball's as a projectile right here, and where it makes an impact with the track again, that's where we see that that slight jump in the velocity.